Bismillah ar-Rahman ar-Rahim. Today we're going to talk about harmonic filter. Harmonic mitigation filter. Harmonic distortion is present to some degree on all power systems. Fundamentally, one needs to control the harmonic only when they become a problem. There are three common causes of harmonics problem. The first one, the source of the harmonic current can be large. Number two, the path in which the current flow is too long, and that will result in either high voltage distortion or telephone interference. Number three, interaction between network and capacitor can cause certain harmonic to be magnified. One of the basic options for controlling harmonic is adding filter to either bypass the harmonic current of the system as it is shown in A. Okay. So over here, this is the source of the harmonic. The harmonic, once we design a filter to get rid of the harmonic that is produced from here, so the harmonic current will go directly to the filter. It will not go to the it will not go back to the source. It will not affect the load if we have over here certain load connected. Okay. The second one, the harmonic filter can block the harmonic current from entering the system. So over here we have the filter, which consists of parallel LC. So we know that at certain frequency the value of JXL will be the same as the value of minus KXC, right? So we have J omega L will be in parallel with minus J 1 over omega C. So now if we find the parallel combination of those at, let us say, at a certain frequency, at a resonance frequency, we're gonna find that that times that, right, over the summation of those, right? So at certain frequency, this value will be the same as this value. So as a result, we're gonna have two values, that and that multiplied, divided by 0, and that will be infinity, right? So as a result, if we have a filter which is designed in this way, that means it will not allow the harmonic current to go through, because at that particular frequency, the impedance of the filter will be just like an open circuit. Of course, the normal current will flow without any problem, but only the harmonic current will not be allowed to flow. So that one we call it blocked. This filter blocks the harmonic current from entering the system. Or we can design a filter, and in this case we call it active filter. An active filter, like what is shown in over here in this diagram. So what we have over here electronic device that will inject harmonic to the system. So since we are using electronic devices, so the filter we call it active. So this filter is called active filter. And again, that will inject harmonic in the system. As a result, if you look at the current that is taken from the source, in this case it will be sinusoidal. Why? Because over here we have harmonic current that will be taken by this non-linear load, and then the remaining of the wave of this waveform, the remaining of this waveform will be injected with this filter. As a result, the current that is taken from the source will appear to be sinusoidal. Okay, so we're going to talk inshallah later on about the active filter. Of course, the active filter is more expensive compared with the passive filter. Okay, so we have passive filter, we have active filter. If we look at the passive filter, we have different design of passive filter. So we can have single tuned filter. So this one will take care of certain harmonic. We can have what we call it first order high pass filter. We call it first order because we have only one capacitor, and this one we call it a second order because we have two elements. We have capacitor and we have inductor. So we have two elements, so that's why we call it second order. Over here we have 1, 2, 3. We have 3 elements, so that's why we call it a 3-order high pass filter. Okay, and this is how the active filter again look like. So the active filter, actually we are utilizing ball electronic device to inject harmonic such that it will compensate the current that is taken by the non-linear load. As a result, the current that is taken by the source will appear to be sinusoidal. As a result, any load connected over here will not be affected by this non-linear load. Passive filter. Passive filter are inductance, capacitance, and resistance element configured and tuned to control harmonics. They are commonly used and are relatively inexpensive compared with other means for eliminating harmonic distortion such as active filter. However, they have the disadvantage of potentially interacting adversely with the power system, and it is important to check all possible system interaction when they are designed. They are employed either to shunt the harmonic current off by providing low impedance path or to block the flow between part of the system by tuning the element to create resonance at selected frequency, as we saw previously, right? Shunt passive filter. The most common type of the passive filter is the single tuned, or they call it notch filter. Okay, so this one, it is used to, I can say, to take care or to shunt one harmonic current only, certain harmonic current. So over here, let us say that you have 5th, 7th, and 8th. So for each harmonic current, you have to design, or you have to place over here what they call it single tuned filter. And this is the most economical type, and it is frequently sufficient for the application. The notch filter is a series LC tuned to present a low impedance to particular harmonic current and is connected in shunt with the power system. Therefore, the harmonic current are diverted from their normal flow path on the line through the filter. Okay, so this is the source of the harmonic, right? Without filter, of course, the harmonic will go to the load and it will affect the voltage level on the network. But once we provide a filter, so the harmonic current will be diverted directly to the filter. Okay, this is one kind of harmonic filter, and you can see that over here we have the inductance. So this part with the coil, it is the inductance, and then those part will be the capacitance. So in this case, the filter designed for medium voltage application will have a dry type iron core reactor position above the capacitor, okay, which are connected in Y configuration with the other phases. Each group of capacitor is fused with the current limiting fuse to minimize the damage in case of failure. So you can see that those are fuses, okay? Those are fuses that are used to protect the capacitor. In outdoor installation, it is often more economical to use air core reactor. Okay, so this one we call it iron core. Part of it is just outside. Then the recommended type of inductance that is supposed to be used will be air core, since it will be more economical. Okay, this is another harmonic filter designed by ABB. So again, you can see the inductance over here. You can see the coil, okay. Then those could be the capacitor bank. And then of course we're gonna have also the some resistance also placed over here. Okay, and again over here we are talking about the notch filter. So the notch filter, it is not only provide I can say a protection from the harmonic, or it will take care of the harmonic, but it will do what we call it power factor correction, since it has capacitor bank. So it will do two functions. It will get rid of the harmonic, okay, harmonic suppression, and it will improve the power factor as well. Okay. And now if we try to plot the relationship between the impedance of the harmonic filter with regard to the frequency. Of course, at the resonance, the impedance will be very small, since JXL will be the same as minus JXC. So as a result, the total impedance will be only the small resistance. And then if the frequency is low, we're going to see that the impedance will be high. If the frequency also increase, then also again the impedance will increase. Another example of a common 480 volt filter arrangement is shown over here. The figure shows delta connected capacitor bank. So those capacitor banks are connected in delta, and then they can be converted to filter by adding reactor, right? So if we add inductance in series with those, then that will convert the capacitor bank to to a filter. And then we can, of course, we can calculate the harmonic order, or we call it H notch, from this equation, where XF will be the reactance of the reactor, and XC will be that one. And of course over here we have delta, we can convert it to Y. So as a result, the equivalent Y of the capacitor, okay, will be equal to XC for delta divided by 3. And again over here, if we look at this diagram over here, or at this circuit, Okay, so over here we have the filter, I can say, because we have the inductance will be and a capacitor will be connected in series. Again, we can convert this one from delta to Y. So for each phase we have L and C connected in series. Okay. Suppose that we use this one in the power system as a filter, and suppose that we have also a source of a harmonic. So this one will represent the harmonic source. And then if we like now to draw the equivalent circuit for the harmonic system, or the equivalent circuit during the if we have harmonic in the system, this is what we'll have, right? Because this one will give us both the source impedance and the transformer impedance. Okay, since we are, as we said before, that the source at the harmonic frequency will be shorted out. Okay, so this one again, it represents both the source impedance and the transformer impedance. And now over here, if we like to plot the relationship between the impedance with respect to the harmonic order or with respect to the frequency, we're gonna find the following. We're gonna find them, first of all, those will create series resonance, right? So the impedance will be very small over there. Okay, then that will be in parallel with that. So this branch, which is the filter, will be parallel with the system impedance, and that will create what we call it parallel resonance, which is this point over here. Okay, so parallel resonance will have high impedance, series resonance will have very low impedance. Okay, also if we, let us say that we don't have over here the reactance, so we are not using this one to be a filter anymore. Okay, we just have capacitor in parallel with the system impedance, and then we have a harmonic source. So again, the resonance will be somewhere over here, which will be again parallel resonance. Okay. So therefore, what is the effect of the harmonic filter? Harmonic filter can create sharp parallel resonant at a frequency below the notch frequency. So the notch frequency, it is the frequency that we choose. It is the frequency that we choose to take care of the harmonic. Okay, that's when we call it the notch frequency. Suppose that we have the harmonic, we like to get rid of the fifth harmonic. So actually, we'll not design a filter to work at fifth harmonic. I will explain that one later on. We design it to work at a harmonic lower than that. Let us say at around 4.7. So as a result, that one we call it detune filter, and that one we call it also, we can call it the notch frequency as well. And we said that also over here, that this resonance frequency must be safely away from any significant harmonic or other frequency component that may be produced by the load. So we have to make sure that this H notch will not be close to a series resonance, to another series resonance, or to any parallel resonance in the system. In many systems with potential series resonance problem, parallel resonance also arises due to the circuit topology, as we saw previously in this slide, right? So over here, we put a filter, to get rid of the fifth harmonic, but at the same time we created parallel resonance. Parallel resonance is formed by the parallel combination between the source impedance and the impedance of the filter. The resulting parallel resonance is always smaller than the series resonance due to the source inductance contribution. The parallel resonance frequency can be represented by the following equation. Okay, so again in this circuit, if we like to find H, which is the harmonic order, so we know that the definition of H will be equal to XC divided by XF, right? But for the parallel resonance, we have now another component, which is XS. So then we need to add XS and XF together and to divide that one by so we need them to add both component. Okay, so it is both the filter inductance and the source inductance. Then the harmonic order will be given as the square root of XC divided by the summation of both reactances for both inductances, for the source and for the filter. Okay, so this is with regard to the parallel, and that is with regard to the series, in which we have only XL and XC. But over here we have both. We have the filter in parallel with the source impedance. So this is our XL, XC, and this is our X source. Okay, of course in this case it is, we call it XF. Okay, so we call it X. We can call it XF just to be consistent with what is written in the equation. So this one will be XF, XF, XF. The interaction with the filter with the source impedance always result in parallel resonance, as we said, characterized by a large impedance peak seen from the capacitor bank upstream. A parallel resonance is to be established at a given frequency. Okay, so of course we can find the frequency for the parallel resonance. So the frequency will be given by 1 over 2 by root LC, right? And in this case L will be actually the combination of both the source impedance and the filter impedance. Okay, so it is the source impedance and the filter impedance. So that will give us the frequency. Okay, but for the series, of course, if we look over here at the frequency, at the resonance frequency, it will be only the two components, right? The L and C only, which is shown over here. Okay, so this is for the series, this is for the parallel. Filters are commonly tuned slightly lower than the harmonic to be filtered. Why is that? To provide margin of safety in case there is some change in the system parameter. So again, if we like to get rid of the fifth harmonic, when we design a filter, we'll not design it at the fifth, at h equal to fifth. We're going to design it at h equal to, for example, 4.7. Why is that? Since we like to provide margin, a safety margin, in case there is some change in the system parameter due to the temperature, due to the aging, maybe some unit of capacitor bank is blown out. So as a result, in that case, there will be a shift in the frequency. So if there is a shift in the frequency, this can move the notch frequency into resonance frequency. As a result, it will increase the amount of current taken by the filter. Okay, so let us say that this is our initial design. Okay, so this is the resonance. Over here we're gonna have a series resonance. Okay, so as a result, the impedance will be very small. So in that case, the current will be so huge. So then no, we said that we're gonna tune this one to be somewhere over here. Okay, to be somewhere over there. So as a result, we're gonna reduce the current at the same time. So as we said that maybe due to the aging and temperature, those value will change, and also that can shift the frequency to there, or it can shift H to be here. So that will of course will just cause very huge current to pass through the system. Of course, we can do that one, but the filter will be very expensive, and we have to so that one should be considered also in our design. But normally this is what they do. So they say that if they have the fifth harmonic, so the filter that is designed will not be designed at fifth, at resonance. They will design it, let us say, at 4.7. Yeah, so this is what we are saying over here. Point number 2. If they were tuned, if the filter were tuned exactly to the harmonic, also this is what will happen. Change in either capacitance or inductance due to the increase in the temperature, due to the failure, due to the aging, may shift the parallel resonance higher into the harmonic being filtered. Okay, so this is also another problem. So that can shift also the parallel resonance into the harmonic that we like to get rid of. So that's why we have to make our design such that it will not be equal to the resonance frequency. It is a little bit lower than that. Okay, and let's say that over here, this could present a situation worse than one without a filter, because the resonance will be very sharp, and definitely that will cause voltage and current to shoot up to very high value. Then how to avoid this problem again? To avoid this problem, with the resonance filter are added to the system, starting with the lowest significant harmonic found in the system. For example, installing a 7th harmonic filter usually requires that 5th harmonic filter should be installed first of all. The new parallel resonance with the 7th harmonic filter alone is often very near the 5th, which is generally disastrous. Okay. The filter configuration does not admit zero sequence current because the capacitor is delta. Of course, over here again we are talking about delta connected capacitor bank. Of course, we know that in delta connected capacitor bank, the zero sequence will keep circulating. Okay. Okay, so over here we are saying that the filter configuration does not admit zero sequence current because the current is delta, because the capacitor is delta connected, which make it ineffective for filtering zero sequence tripling harmonic. Okay, so those harmonic will keep circulating through delta. Because the 480 capacitors are usually delta configured, other solution must be employed when it becomes necessary to control the zero sequence third harmonic current in an industrial and commercial building facility. Okay, so that means if they place the capacitor as connected and they have a problem with the third harmonic, so of course they have to find a way such that they will get rid of this third harmonic, because with the existing delta capacitor that will not be effective to take out the third harmonic. In contrast, capacitor in utility distribution system are more commonly wide connected. This gives the option of controlling the zero sequence tripling harmonic simply by changing the neutral connection. So if of course if the capacitor bank are not connected, it will not get rid of the third harmonic. So in that case, it has to be reconnected to be delta, to be Y. Placing a tap reactor in the neutral of the capacitor is a common way to force the bank to filter only zero sequence harmonic. This technique is often employed to eliminate telephone interference. So this is the way how to get rid of the third harmonic. So they will connect the capacitor bank as Y, and then the neutral will be connected also through a reactor in order to limit the telephone interference. So if they just connect the neutral to the ground, so that will pass very large third harmonic current through the ground. So as a result, that can cause interference. Okay, let us now look at this example over here. So over here we have single tuned filter. So it is tuned to 13. So H equal to 13, and XC is given. Say calculate the filter elements, then plot the filter impedance. Assume that the quality factor to be 100. So what we'll have to do, we'll have to find what will be the value of L, what will be the value of R. So of course we know H, right? We know XC. So we know that XL will be equal to XC divided by H squared, so that will give us XL. Now to find the resistance, we know that Q, the quality factor Q, is equal to X N or XR, or Xn divided by the resistance, right? Xn will be square root of XL and XC, and Q is given as 100, so that will give us the value of R. Now to plot the impedance against the frequency, of course we have to write it as a function of the frequency or as a function of the harmonic order. We can take the magnitude, and this one will be the result. Okay. So we like to get rid of the 13th harmonic order. Before that, the impedance will be mainly capacitive. After the resonance frequency, it will be mainly inductive. Okay, so this so the total impedance at resonance will be R, even if R is not available. Of course, since over here we have the inductors are made from wire, so that will have also some resistance. So say that typically the resistance of a single tune harmonic filter is the intrinsic resistance of the reactor. However, R can be favorably used to vary the quality factor of the filter and provide a way to control the amount of desired harmonic current. The second example say that which harmonic will be trapped by the filter comprising 4 single branch with 3 phase 50 Hz 400 volt Y connected. So we have I can say 4 filter. We have 4 of them. They consist of inductor, capacitor, and resistor. Okay, so we have four of these. The reactive power for the first filter is 30, so Q reactive will be 30 kilovolt ampere reactive. For the second will be 20, for the third 20, for the fourth will be 20 kilovolt. And we have those value are given for the inductance. Okay, so those are the inductance for the four single tuned filter. Okay, he said that to plot the filter impedance if the resistance for each branch are given as follow. Okay, so anyhow we like to find the filter parameters, and then we like to plot the impedance. Just like what we did before, so we know that H will be equal to XC over XL. So L is given, then we can find XL, let us say at a given harmonic. XC also is given since we know the voltage, so we know that XC will be equal to V square over the reactive power, right? So the voltage is given, reactive power is given, so we can find XC. Then we can find H. Okay, and then from there we can find the harmonic order for each filter. Okay, the solution of course is given over here. Okay, so this is the way to calculate X, the value to calculate H. So for the first up to the fourth filter, Q, XL, L, XC, and then we know H. Okay, so this is it is used to tune the fifth harmonic, but of course we didn't tune it at fifth because of the reason that we have already discussed. We tune it to be at 4.67. This is it's supposed to do the seventh, but we did it at 6. This one's supposed to do 11, but we tuned it at 10.45, 13, but we did it at 12.39. Okay, and that will be the different system impedance. So you can see the harmonic order for each impedance of the filter. Then also you can find the overall impedance if you like. Okay, let us look at example number 3. Say that assume that a series filter is tuned to be to the fifth harmonic. Okay, to the fifth harmonic, and it is going to be installed to low voltage bus bar. So we have a transformer, high voltage, low voltage. In the following system, determine the filter characteristics. So again, we need to find L, C, and R. So once we find the filter characteristics, we need also to find what? To find the parallel resonance condition. So we have over here series resonance, okay, and because we have transformer with a certain impedance, we have the source with a certain impedance. So for the harmonic order, those will be in parallel, right? So we're gonna have R. This is for the harmonic. Then over here we're gonna have the inductance that include the transformer. So this one will be X for the transformer plus X for the source. Okay, and over here we have the equivalent circuit for the harmonic. Okay, So we're gonna have over here series resonance, then over here we're gonna have parallel resonance. Okay, so we can calculate, of course, the impedance of the capacitor. Okay, we are given Q, we are given C, so we can find XC. We can find XL because we know that H will be equal to the square root of XC divided by XL. So this is calculated, this is given, then we can calculate also XL for the harmonic filter. Okay, the resistance, to find the resistance, of course we need to have the quality factor. It is not given, we can assume it to be, let us say, 100. So that will give us the value of the resistance, right? We can calculate the impedance of the transformer. So the per unit value is given. Then we can calculate the X for transformer base. Let us find the base value. So the base value will be equal to V square, which is 0.4 divided by S base, which is 2. So that will give us X base or Z base. We multiply that one by the per unit, and that will give us X for the transformer. Therefore, we can calculate the reactance of the transformer. For the reactance of the source, we are given also the megavolt ampere. We are given the voltage. So then we can find the value in ohm. So it will be 15 squared divided by 20. So that will give you the impedance in ohm. We can transfer it to the to the low voltage side. So we multiply it by 0.4 squared divided by 15 squared. Or you can find the base and then we transfer it again. Okay, so this is how can we solve the problem. We calculated XC, then we calculated XL, we calculated XR, or we call it XN sometime, and then we can find R. So this is with regard to filter. This is with regard to the transformer. We calculate Z base or X base, we find it. Then we calculate the impedance of the transformer in ohm. And we do the same thing with the source. So over here, if we like to find the harmonic order for the parallel circuit, okay. So as we said that, we have XT, XS parallel with the filter, right? So to find the harmonic order for the parallel resonance, of course, it will be again XC but divided by XL for the filter plus XT for the transformer plus XS4 for the source. Okay, as it is done over here. Okay. Then we can, of course, find the total impedance of the system. So as a result, the filter will be in parallel for the harmonic, okay? For the harmonic order, the filter will be in parallel with both the source and the transformer. And that will be the result. And then we can sketch the impedance with respect to the harmonic order. So this one will be the impedance of the filter, okay, and this one will be the impedance for the whole system, okay. So that includes both filter as well as the transformer and the source impedance. This is example 4. We have 33 kilovolt 6.2 megavar capacitor bank to be installed at the bus where the short circuit level is 750 megavolt ampere. Investigate the resonance and then how to avoid the resonance problem. Okay, so what we have a bus working at 33 kilovolt, and over here what we have installed capacitor bank. The size of the capacitor bank is 6.2 megavar, so Q for the capacitor is 6.2 megavolt ampere reactive. And over here we have the system impedance. Okay, and the short circuit level is 750. So from here we can calculate XL. Well, we know that XL is can be calculated from the short circuit level and from the voltage. Okay, so the so XL will be equal to XL, or we call it XS, will be equal to V square over the short circuit level. That will be 1.42. Okay, and we know that the how to calculate the reactance of the capacitor. V square over also Q over the reactive power, that will be 175. Now we can calculate the harmonic order, or the resonance. So it will be XC over XS, and that will give us 11. Now it say that let us design a filter to trap the 11th harmonic by adding a reactor in series with the capacitor. So now we like to trap this harmonic that will result, of course that will be during the parallel resonance, because if we draw the circuit diagram for the harmonic, we will have a capacitor in parallel with the source impedance only, right? Okay, so now how to get rid of this one? We can get rid of this one by having a filter. So what we can do, we can add with the capacitor bank a reactance, and the value of that reactance can be determined from the harmonic order and from the value of XC, so that will be 1.42. And then to find the resistance, suppose that the quality factor is given as 60, then we can determine the value of R from this equation. So the value of R will be given as Xn over Q, and Xn it is the characteristics impedance, or XR, which is the square root of XL times XC, so that will be 17.9, and then we can calculate the value of the resistance. Now if we plot the impedance, the magnitude of the impedance with respect to the harmonic order H, we're gonna find the following, that so there will be series resonance course at 11, because this is what we like to do, because we're gonna have 7 order harmonic, and we're gonna have 11 order harmonic, and we like to get rid of that 11th order, so that's why we design a filter. And then the value, the magnitude of the impedance, of course, will go up at lower frequency, and then it will go up again at a higher frequency, because over here the dominant part will be XC, over here the dominant part will be XL. Okay. Again, we know that in single tuned filter, the relationship between the quality factor and the resistance and the characteristics impedance, it is given at this equation. So QS will be equal to XR over R. This is for the single tuned filter. Okay, So we say that usually the value of R is only the resistance of the inductor, which result in a very large value of Q and a very strong filtering. Okay, so normally R will be the resistance of the wire that is used to make the inductance. However, it might be required to have some losses to be able to dampen the system response. So how to dampen the system response? Of course, we have to put more resistance. So to achieve this, the resistor is added in parallel with the reactor to create what we call it high pass filter, which is given in this diagram. Okay, so we add over here with the inductance a resistance in parallel, and that will create what we call it high pass filter in this case. And of course, to find the total impedance, it will be the resistance in parallel with the reactance, and then both will be in series with the reactance of the capacitor. And the cutoff or the current frequency can be obtained from this relationship. So we have L, we have C, and that will determine the corner frequency. With regard to the quality factor in this case, for such kind of configuration, to find the quality factor, so the quality factor can be obtained from R over XL or R over XT, and the typical value for quality factor will be range between 0.5 to 5. Okay. So in general, if we like to find the quality factor for any harmonic for the second order high pass filter, then the quality factor will be given as R divided by XL, of course, times the harmonic order. So this one, this is the way how can we calculate the quality factor for the second order passive filter. And to design a second order damped filter tuned to the H tuned harmonic, so we have to do the following. First of all, we have to decide about the capacitor size in megavar, calculate the reactance of the capacitor from the reactive power, then find the size of the reactor, the inductive reactance from the harmonic order and from the value of the capacitance of the reactance of the capacitance. Then we can calculate the characteristics impedance by multiplying XL times XC, or it is equal to H times XL or XC over H. And then we can determine the value of the resistance by multiplying H tuned times quality factor. And then we can determine the rated size for the filter, which consists of again R parallel with L in series with C. So it will be the voltage square divided by XC minus XL, or H tuned square or H tuned square minus 1 time the reactive power of the capacitor. Give the impedance function of the filter, okay, as is given in this equation. And now let us look at this example over here. So we have second order damped filter is to be tuned for h greater than or equal to 13. If xc is given as 2.5, calculate the size of the reactor. So we like to calculate the value of xl. Okay, so we know h, we know xc, then we can determine xl directly, right? Calculate the characteristics impedance, which is called h tuned, or we can call it hn. So in this case we call it h tuned. So h tuned will be either square root of xl times xc, or hxl xc over h. Determine the size of the resistor for a quality factor that range between 0.5 to 5. So resistance will be equal to the x tune time quality factor. So that will give you the range of the resistor. In example number 6, we have two series filter tuned to 7th and 11th. Okay, so we have over here one tune circuit filter, another tunes single tune filter, and then we have damp filter, okay, which consists of course capacitor and then inductor and resistor. So we have those kind of filter that added to the system. Okay, and the this voltage of this bus is 36 kilovolt, and the reactance and the value of the reactive power for the capacitor bank, it range from 5 to 2. So we have 5 for the first filter, 2 for the second filter, and then 2 megavolt ampere reactive for the damped filter. Okay, so that is the so this is given again. This is given to us, and the value of Q is also given to us. Okay. So now he told us also what we need to do. Design the filter. So we need to make filter design. That means we need to calculate what will be the value of XC, what will be the value of XL, what will be the value of the resistance. So those are the unknown for different harmonic order, 7, 11, and 17. Okay, so for the XC, the voltage is given, the Q is given, then of course we can calculate XC. Once we know XC, once we know H, we can calculate XL. XN, square root of XT times XL, and then you can find R from the quality factor, right? So we know that quality factor will be given as R over XN. So then R will be Q times XN. So over here we need to calculate XN. So if you multiply Q times XN, that should give you the value of the resistance. Okay, of course everything is given again over here. Okay. For the series passive filter is shown over here. So in series passive filter we have L, we have C. They are connected in parallel, but of course the filter is connected in series in the network. It is not connected in shunt with the network. So let's say that unlike a notch filter, which is connected in shunt or in parallel with the network, which is connected in shunt with the system, a series filter is connected in series with the system, with the load. Okay, so it is connected in series with the load. The inductance and the capacitance are connected in parallel and are tuned to provide a high impedance at selected harmonic frequency. So at a certain harmonic frequency, XL will be equal to XC. As a result, the circuit will be like an open circuit. As a result, the high impedance will block the flow of harmonic current at that particular frequency. Whereas at fundamental frequency, the filter would be designed to yield a low impedance, and that will allow the fundamental current to flow with only minor additional impedance and losses. A series filter are used to block a single harmonic current and are especially useful in single phase circuit. The use of series filter is limited in blocking multiple harmonic current. Each harmonic current requires one series filter, which is tuned to that harmonic. This arrangement can create significant losses at fundamental frequency. Like other series components in power system, a series filter must be designed to carry the full rated load current and must have an overcurrent protection. Therefore, series filter will be less commonly applied compared with the shunt filter. One common application of series filter is in the neutral of the grounded Y capacitor to block the flow of the turbulent harmonic, while still retaining a good ground at the fundamental at fundamental frequency. Okay, so this is what the series filter is doing. Multiple stages of both series and shunt are often required in a practical application. For example, in shunt filter application, a filter for blocking a seventh order harmonic would typically require two stages of shunt filter: the seventh harmonic filter itself and the lower fifth harmonic filter. Similarly, in series filter application, each frequency requires a series filter of its own. Therefore, multiple stages of filter are needed to block multiple frequencies. So if you like to block several harmonic, then of course in that case you need to have several stage of series filter. In numerous power system conditions, harmonic can appear not only in single frequency but can spread over a wide range of frequency. A 6-pulse converter generates characteristics harmonic of 5, 5th, 7, 11. Electronic power converter can generate time varying interharmonic, covering a wide range of frequency. Designing a shunt or series filter to eliminate or reduce these would be very difficult using shunt or series. Therefore, alternative harmonic filter must be devised in this case. A low-pass broadband is ideal application to block multiple or widespread harmonic frequencies. A typical configuration of a low-pass broadband is shown. A current with a frequency component below the filter cutoff can pass. Current with a frequency component above the cutoff will be filtered out. Since this type of low-pass filter is typically designed to achieve a low cutoff frequency, it is then called low-pass broadband filter. In distribution system application, the effect of low-pass filter can be obtained by installing a capacitor bank on the low voltage side of the transformer. The size of the capacitor bank would have to be selected to provide the desired cutoff frequency when combined with the transformer leakage inductance and the system impedance. It is then capable of preventing harmonic above the cutoff from penetrating the high voltage side of the transformer. Okay. Since the cutoff can be sometimes quite low, the size of the capacitor bank may be large. This will result in a significant voltage rise. Should the voltage remain high, the voltage regulator or transformer load. What we mean by C filter? C filter are alternative to low-pass broadband filter, and it will reduce multiple harmonic frequencies simultaneously in industrial and utility system. They can attenuate wide range of steady state and time varying harmonic and interharmonic frequency generated by converter, induction furnace, and cycloconverter. The configuration of C filter is nearly identical to that of the second order high pass filter. So this is the second order high pass, this is the C filter. The difference is only over here they add a capacitor. And now if we look at the impedance response of the C filter, it is shown over here. So again over here we have a series resonance over there, which is shown over there. Then the combination of the system with the combination of the filter with the system reactance that will make parallel resonance. A practical consideration in the use of the passive filter. So passive power harmonic filter design require a number of practical considerations. There is no unique solution to the design problem. So in each case, a careful trade-off analysis must be performed. Practical considerations include the following. With respect to tuning, the harmonic filter section are tuned below the harmonic frequency, as we said previously, to prevent the filter frequency from shifting upward. If one or more capacitors fail and their fuse is blown, typical order are 4.85 for the fifth harmonic. So if we like to get rid of the fifth harmonic, the filter is tuned to 4.85. If we like to take out the seventh, we tune it to 6.7 and so on. And as we said that this is in order to prevent the filter frequency from shifting upward, and then it will coincide with the resonance. Okay, we don't like that situation to happen. Okay, of course, if it happens, then the value of the current that passes through the filter will be so huge. Then in that case, of course, that could cause problem to the filter itself and to the capacitor, of course, mainly to the capacitor bank. A protection. Capacitors are protected by fuses. Okay, and they are placed in a small group to minimize the effect of fuse blowing. The whole filter can be divided into assemblies, each protected by circuit breaker. Location. Filter should be located electrically close to the non-linear load that produces the harmonic current. Okay, so the filter, if we like to design a filter to get rid of the harmonic that is generated by a certain load, so a filter should be located near the load, near that non-linear load that will generate harmonic. Switching. Filter provide fundamental frequency reactive a portion of the filter can be switched off at time of light load to limit the over voltage. Okay, so one function of the filter, of course, as we said, they can be used to improve the power factor, since they are providing reactive power. So during the light load, the voltage level will be normally high. So if the capacitor remain in the system, that can increase the voltage to a value that exceed the recommended limit. Tolerances. Capacitor and inductor must be specified so that the combination of rating does not result in resonance at an undesired frequency. In other words, we don't want positive peak in the filter impedance curve to correspond with the harmonic frequency. Rating. The current rating of the inductor and the voltage rating of the capacitor must include both fundamental and harmonic component. Okay, so again, this is when we select or when we design the system, we have to consider not only the fundamental, not only the harmonic, but both should be considered. Detuning, which is a change in a system impedance or component variation due to aging or temperature, can result in some detuning of the harmonic filter. That means if we design the system, let us say, to run, as we said, at 4.7 or 4.8, then it can run due to the aging at a value which is different from 4.7. Active filter. So this is the active filter. So active filter actually is made from power electronic devices. Okay. So over here, suppose that we have a nonlinear load. So as a result, the current that is taken by this nonlinear load will not be sinusoidal. So if we don't have active filter in the system, So that means the current also that is taken from the source will be also nonlinear. So as a result, that will affect the voltage at the different buses. Okay, harmonic will be created. But over here, what we are doing, we are connecting what we call it active filter. Active filter will provide the harmonic so that this one, the current that is taken from the non-linear load, it is non-sinusoidal, and then that one will be compensated such that the main current taken from the source will be sinusoidal. So that means if we add that component with that, so adding those two components will be equal to the current taken from the source. So as a result, anything connected over here will not be affected by the nonlinear load. Okay, so that means, for example, if we have over here any load connected over here at a certain bus, it will not see those nonlinear current that is flowing through the nonlinear load. So the active filter are sophisticated electronic based device for eliminating the harmonic. They are much more, of course, expensive compared with the passive filter. They have distinct advantage that they don't resonate with the system, so we should have no problem with the resonance. Okay, don't forget that in the passive filter we have capacitor bank that will resonate with the system. The basic idea is to replace the portion of the sine wave that is missing. Okay, so to replace the portion of the sine wave that is missing in the current which is taken by the nonlinear load. An electronic control monitor the line voltage and or current, then it will switch the electronic very precisely to track the load current or voltage and to force it to be sinusoidal. Okay, so any missing component will be provided by those electronic devices such that the current taken from the source will be sinusoidal. One type of active filter is shown over here in this figure. Note that the nonlinear load draw harmonic current IH. Okay, so this is over here, we have nonlinear load. Take this current from the source, then the active compensator sends the harmonic current and inject the compensation current IC. So this is what will be injected in the system such that the current taken from the source will look sinusoidal. Okay, those are some typical example with respect to the type of load. If we have, for example, single phase power supply, the nonlinear load will draw such kind of current. But if we add active filter, this is how the supply current will look like. Semi-converter, again this is the current taken, but with active filter this is how the supply current will look like. AC voltage regulator with RL load, okay, this is how the current will look like. That is taken from the supply. AC regulator, resistive load, 6-pulse converter, 6-pulse drive, 6-pulse drive voltage source inverter with 30% AC input shock. There are mainly two types of active power filter. So there is what we call shunt active filter. Okay, so it is connected in shunt with the system. And we have another type which is called series active filter. So the one which is shown over here is the shunt. The one which is shown over here is the series. Okay, so we know that the terminal of the filter are actually connected in series with the source. So the shunt active filter is used to filter the line current, and the series active filter is used to filter the line voltage. So that is used to filter the line current connected in parallel. This is used to filter the line voltage connected in series. It's also possible to combine both types to filter both current and voltage. The following are the advantages of the active filter. Superior filtering performance. Active filters are generally under microprocessor control and hence can be tuned to particular application. The filter can be tuned under microprocessor control if, for instance, the system impedance changes. So the change in this can be detected, and then again the microprocessor control will do the required adjustment such that the filtering process will be very smooth. Small physical size. The high switching speed of devices allow energy storage element to be of smaller weight and volume. Okay, since we are using electronic device, so the size of those elements will be small. Flexibility, they are more flexible in application compared with the passive filter. Of course, the advantage of active filter must be weighted against the extra design time and cost. It costs more money, it needs more time to be designed. Sometimes we can have a combination of both passive and active filter, and in that case the filter, we call it a hybrid harmonic filter. So the application of the harmonic filter, including both passive and active, of course, has been proposed in so-called hybrid. In this method, harmonic reduction and reactive power compensation is shared between a passive and a modest active filter. Typically, the active filter section is rated at a few percent of the load kilovolt ampere. A typical power system. So over here we have a power system transformer, and we have over here the passive filter. Okay, we have over here nonlinear load, as we can see, and we could have over here also motors. A simplified version of power system is shown in the figure. The power factor correction capacitor has been converted to a series tuned passive filter. Okay, so over here the function of this capacitor bank is to provide reactive power and to improve the voltage level. Now it is converted to be a filter with the addition of the reactor. In the non-linear load, for example, an adjustable speed drive require a fundamental frequency current for operation, but can be represented as the source of harmonic current into the system. Okay, so this is the adjustable speed drive, which is considered to be a non-linear load. Okay. The path of the harmonic current produced by the nonlinear load will be shown in this diagram. So the harmonic current and voltage are described as the following. IH, which is the harmonic source of the converter. Okay, so this is the converter. Converter is providing harmonic. The IHF, the filter harmonic current. Okay, so this is the filter. This is the harmonic current that flow through the filter. The harmonic component injected into the point of common coupling, we call it IHC. Okay. So we have a harmonic source. We have a filter that will take care of the harmonic, but we could have also a small portion of this harmonic that will be injected in the source or into system. The IHR is the equivalent passive motor load current, so this motor needs a certain current. The harmonic current component returned to the utility source, we call it IHS. So over here we have the harmonic current that will go back to the source. VHC is the harmonic voltage component at the point of common coupling. So we have VHC called the harmonic voltage component. Harmonic filter design limitation. Equipment withstand capability. According to existing equipment standard, harmonic should be limited to the equipment withstand capability. Like what we discussed already in the transformer, that if the transformer is designed to provide power to the normal equipment, then of course based on the size of the equipment, then we can choose the transformer size. But if the transformer is utilized to provide power to equipment or to a nonlinear load that will generate harmonic, then of course we have to consider that one. Okay, so as we said that we need to derate the transformer. So if the load, let us say it needs 100 kilovolt ampere and it has harmonic content, then we cannot choose 100 kilovolt ampere transformer. We have to choose transformer bigger than that. Okay, so over here let's say that when transformers are operating at rated load, the total harmonic current distortion should be limited to 5% according to IEEE standard C57-2000. And IEEE standard C57-98 define the method for derating transformer when supplying the non-sinusoidal load. Based on IEEE standard 103692 and IEEE standard 18-2002 state that capacitors are intended to be operated at or below their rated voltage. Capacitors shall be capable of continuous operation under contingency system and bank condition, provided that none of the following limitations are exceeded. The first one, the rated of the capacitor should not, or the capacitor should not exceed 135% of the nameplate kilovolt ampere. That means if we have a capacitor that is written on that capacitor, let us say 100 kilovolt ampere, then that capacitor should not be operated more than 135 kilovolt ampere. Number two, with regard to the root mean square voltage, the voltage should not exceed 110% of the rated root mean square voltage, including harmonics, of course. With regard to current, 135% of the rated current, including also harmonic. And also the peak voltage should be limited to 120% of the peak voltage of the capacitor, including harmonic. Okay, so those are the IEEE standard for shunt power capacitor. Filter design and procedure are detailed in the steps shown below. Okay, so over here now we're gonna explain to you how can we design a filter. What are the steps that we need to follow if we like to design a filter? And let us start with this example. Let's say that we have single tuned notch filter will be designed for industrial facility and applied at 480 volt 60 Hertz bus. The load where the filter will be installed is 1200 kilovolt ampere with a relatively poor displacement power factor of 0.79 lagging. It is desired to improve the power factor to 0.98 lagging. Using this designed filter. Okay, so what we like to do over here, we like to place a filter that will get rid of the harmonic, and also at the same time it will improve the power factor. Also, let's say that the total harmonic current produced by this load is approximately 30% of the fundamental current, with maximum of 25% fifth harmonic. So the fifth harmonic current will be 25% of the fundamental current. Okay, so those are the specification. So if we just summarize what is written over here, so we have a 480 volt bus, and over here we connected a load, and the specification of this load are it has 1200 kilovolt ampere. This load is working at 0.79 lagging power factor. Okay, and now we like to improve the power factor of this load, and also to remove the harmonic by using single tuned notch filter, such that the power factor will be improved to 0.98, and also the total harmonic current produced by this load will be mainly the fifth harmonic, and it is limited to 25% of the fundamental current. Okay, furthermore, say that also the facility is supplied by a transformer with 6% impedance. The fifth harmonic background voltage distortion on the utility side of the transformer is 1% of the fundamental when there is no load. The harmonic design procedure approval. Okay, so also the what we have over here, also we have a transformer that feeds the load as we said. Okay, so this transformer will have 60 of 0.06 per unit, and it has S of 1500 kilovolt ampere. So from here we can calculate the impedance of the transformer in ohm, and this voltage, of course, it is 480 volt. It is equal to V square divided by 150 10 to the power 3 times 0.06, so that will give us the transformer impedance in ohm. Okay. And also he said that the what we have over here is also we have fifth harmonic background voltage distortion on the negative side of the transformer is 1%. Okay. Also he told us that we have over here distortion on the voltage of the transformer. Okay, we have distortion, and he said that the fifth harmonic of the voltage is equal to 1% of the fundamental voltage. Okay, so we have also voltage distortion over here. Of course, I mean V divided by impedance, that also will affect the or that will increase also the harmonic current that flow through the load. Okay, so again, those are also some additional information that are provided to us. Okay, so now let us look at let us move step by step to solve this design problem. Okay, so as we said that the system parameter are given. This is the summary. Okay, so the size of the load, the current power factor. Okay, the harmonic current, 25% of the fundamental current, the size of the transformer, the impedance of the transformer, and then we have also at no load there is a fifth harmonic voltage distortion in the utility, which is 1% of the fundamental. Okay, so this is the information that is given to us. So the first step is to do filter tuned frequency selection. Okay, so filter tuning frequency selection depends on the harmonic characteristics of the load. For the single tuned filter under consideration, the filtering starts at the lowest harmonic frequency generated by the load, which is the fifth. Okay, so in this example, the lowest harmonic frequency is the fifth. And of course, as we have discussed it already, that the filter normally is tuned at slightly lower frequency than the desired tuned frequency because of the following reason: to allow for variation in the system impedance and tolerance in the filter components. So as we said that the capacitor bank could be blown, the fuse that protect the capacitor bank could be blown due to the aging, due to the temperature. So the filter elements could be vary. To minimize the possibility of dangerous harmonic resonance if the system parameter change, and that will result in a shift in the tuning frequency. Okay, and to prevent the filter from acting as a short circuit for the offending harmonic current. Okay, so if you have fifth harmonic and your filter will make a short circuit at fifth, of course the current will be so huge, so So then the cost of the filter will be so high, because you need to make sure that all components that will be in the filter will carry this huge current. And so as a result, we are not doing it at the, for example, at the fifth. We are doing it below that, in order to reduce the duty on the filter element or component. Okay, so so those will be the filter parameters. So we have, because he told us it is a single tuned filter, so it will consist of both inductor and capacitor. Okay, you can consider them to be connected in this way, or it could be connected, I mean the capacitor will be connected in series with the inductor, and then we're gonna have Y connected filter, or it can be as a delta as it is shown